Hi, howdy y'all. So we're going to start the presentation on convolution. So we're going to begin with just the basic definition. If we have two measurable functions on our n, then we define f star g of x to be the integral of f of x minus y gy dy. So this is going to be a function of x, and we're integrating with respect to y. And this is called the convolution of f and g, okay? So one thing that we have to note right off the bat is that we know that we have to use, to make this a well-defined operator, we need to use theorem or proposition 212, which states that if G is an m bar measurable set, where again this is the completion of the measure. So if f is a measure, measurable with respect to the completion of m on x, then there exists an m measurable function on x that we're going to call g, such that f and g are almost everywhere equivalent with respect to the closure of the completion measure. So what this tells us is that because x minus y is continuous, we get that it's measurable. And we know that f is measurable. And again, this is all with respect to the Lebesgue measure. The Lebesgue measure, however, is the completion of the Borel measure. So what we can do is we can say that there exists some f naught that is Borel measurable. And such that f equals f naught almost everywhere with respect to Lebesgue. With respect to the Lebesgue measure. So because they're almost everywhere equivalent with respect to the Lebesgue measure, we can swap out this. With respect to our definition, I can swap out, because we're taking a Lebesgue integral, I can swap out f with f naught. And now we have that this is equal to f naught g. And this guy is Borel measurable. So we get that the composition of it in the continuous function x minus y is also Borel measurable, which means that it's Lebesgue. So this is in fact Lebesgue. So this Lebesgue integral is well defined, even though we don't from this argument don't necessarily get that f is Lebesgue measure. F compose x minus y is Lebesgue measurable. We do get that it's equivalent to almost everywhere to a function that is Borel measurable and hence Lebesgue measurable. So we can always take the convolution of two Lebesgue measurable functions where we just say that the definition of it is with respect to replacing the f with its almost everywhere equivalent Borel measurable function that's guaranteed by proposition 212. So that's just a quick technical note that this is in fact a well-defined operator on the Lebesgue measurable functions. We just have to do this little trick where we take it up to some type of equivalence class. So several properties follow directly from the definition. So we're going to assume that all these integrals exist. So if this is the case, first we're going to have commutativity, then we're going to have associativity, then we're going to have translation invariance. More specifically, it is translation invariant with respect to both variables. So if I've got my translation z, this is going to be the same thing, tz, then this is going to be the same thing as doing the translation on f or doing the translation on c. Lastly, we're going to get that if we take the Minkowski sum of the two, of the support of f and the support of g, and we call it A, so the sum of all vectors in both supports, then this is going to, then we get that the support of the convolution is always a subset of that Minkowski sum. So, so we're going to run through these proofs real quick. I've got them all written up here. Okay. So the first one, we're going to do basically the same trick that we do in Calc 2, with making sure this is still visible. Okay, good. We're going to do the same trick that we did from Calc 2 with U substitution, basically. We're going to let z equal this x minus y thing, but this would tell us that y is equal to x minus z. So then we get that the convolution of f and g is equal to, by definition, the integral f x minus y, g y. Then we're going to replace the x minus y with z, and we're going to replace the y with the x minus z here. Now, just like with U substitution, this is also going to force us to replace the dy with the dz. And now we get that this is just the definition of f composed g because multiplication is commutative. So because I can swap these guys, we get that this is just the integral of g x minus z dz, which is exactly the definition of that with respect to x. So we get commutativity. For associativity, it's going to be basically the same thing, except we're going, so once I expand out the integration, what we notice is that this is, with respect to dy, then dz, then by the, Tolini, I think, how do you pronounce his name? What was his name? The Tonelli, Tonelli, Tonelli theorem, we can reverse the order of our, integrations. And since this is symmetric with respect to, since g is the same in both, this is not going to affect g. We can swap them out, and we get that is, in fact, in the opposite order. So we get associativity as well, following directly from the Tonelli theorem. Lastly, or sorry, second class, we have 3 with the translations. So we're going to expand this guy. Now we remember that this is a function of x. So what this translation tau of z is really doing is we're going to be subtracting z from x. So we're going to slap that in there. And if you look at the definition, there's only one x in the integral. So the only place that we're going to end up with the negative z is right there. However, this is exactly the definition of tau z f of x minus y. So right there, we swap that in there, and we now have that tau z f of x minus y, gy, is a composition of functions. So this is the same thing as saying the convolution of tau z f with g. Now, to get the second part of the theorem, which says that it is also true for tau g, we do this by commutativity. So once we have our statement here, tau, so by commutativity, if we have tau z of f convolution g, all we do is note that this is commutative, so we can swap the order. And then this first argument works again, and we have that tau z of g convolute f is the same thing. So this follows directly from commutativity, and this guy follows directly from the definition of the translation, and then from the definition of convolution again. Lastly, we're working with the supports. So we say that if x is not an element of A, and again, remember that A was defined to be the Minkowski sum of the supports of f and g. So the sum across all of the vectors, x plus y, where x is in the support of f and y is in the support of g. So if we take something that's not in that set, x is not in A, then this implies that if y is not in the support of g, then x minus y will not be in the support of f, because x being in A implies that x not being in A implies that there's no way to sum y and x, y being in the support of f, y being in the support of g, and some other A being in the support of f. There's no way to sum y and A to get x. So if y is in the support, then this would imply that the difference between them is not in the support of f by definition. So since then what we have is f of x minus y gy, well, this is not in the support of f. So in fact, it must be 0, which makes the product 0 for all y. So we get that the convolution of f and g is not 0. But this is exactly saying that this is that x is not in the support of the convolution, which would imply that the support is in fact a subset of A. So that gives us our 4 basic properties that the book discusses. Next video, we're going to open up with the first theorem, which I believe was theorem, where was it? Theorem 8.7. So these here are theorem 8.6. 8.6, teorema. If you're interested, 1 through 4 are theorem 8.6. Okay, I will see you guys in the next video.